afternoon, or good morning for our audience here in China. Welcome to this Earth Data webinar. Today it's our great pleasure to have Professor Samantha Hansen speak with us from University of Alabama. So Samantha got her PhD a while ago at UC Santa Cruz, and she has been working at various institutions, but spent most of her career at the University of Alabama. And she, in recent years, I think probably in recent decades, she has been working on the project that using the seismic observations, particularly in Antarctic regions, to explore the Earth's core-mantle boundary seismic anomalies. And so today she's going to share with us the progress that her team has made in that direction. So normally our talk goes for 40 to 45 minutes, but since this webinar is a bit flexible, and then we have leave for 15-20 minutes for interaction with our participants today. And as we agreed earlier, so this talk will be recorded and posted on the CG Earth Data webinar to Advanced Science. And also for people who sign in our channel but could not make the time today, can watch this video to know more about URBZ. So Samantha, there you go.
Oh, sorry. I was just checking the slides. All right. Well, thank you very much for the introduction. And I appreciate you guys having me to give this talk today. As mentioned, I'll be talking about what are known as ultra-low velocity zones, or ULVZs, beneath Antarctica and the Southern Hemisphere.
Recording in progress.
Yes, we got it. Thank you. But before I get too far, I'd just like to take a minute to acknowledge my co-authors. This includes Coyote Agbula, who was recently my master's student, and he's now gone on to pursue his PhD at Cornell. Edgar Nero, Mingming Li, and Sang-Hyun Shim, who are all at Arizona State University. And also Sebastian Rost, who's at the University of Leeds. And I'll also mention that this work was financially supported by the National Science Foundation. So this cartoon represents how we typically illustrate the interior of our planet, both to our intro geology classes, as well as to the public at large. The inside of Earth is generally represented as this series of concentric shells, each of which is roughly homogeneous in composition. So of course we have the outer crust, this thin layer of our planet, this thin outer skin that we live on. We have the underlying plastic mantle, which has both upper and lower components, the metallic molten outer core, and then the solid metallic inner core. And along with this concentric shell view of our planet, this is an example of how we often present plate tectonics to people. Indeed, I pulled this from one of the US Geological Survey websites. So just briefly, places where we have hot material, that material is buoyant and it's going to rise, giving way to things like hotspot volcanism and mid-ocean spreading centers. And where things are cold and dense, they're going to sink, such as what's happening here at these subduction zones, where we're basically recycling oceanic lithosphere back into our planet. And then, as illustrated by the orange arrows, the whole system is driven by convection in the mantle, again, caused by temperature differences between the deep mantle and the shallow mantle. So this and the previous slide are useful ways to describe the interior structure of our planet to people, but they're not the most accurate ways to represent the structure. And particularly over the last 20 years or so, we've made some really interesting progress with geophysical studies, particularly seismology studies, to look at the details of what's happening inside the Earth. So this animation illustrates that when you have an earthquake, that event sends out seismic waves, shown here in blue and in red. And those waves are going to move through the entire interior our planet, sampling all those different layers that we looked at in the previous slides, as well as any other interesting features beneath our feet. Also, over the last 20 years, we've drastically increased the number of seismometers or sensors that are distributed around the planet to record the waves that you're seeing here. And so together, this is allowing us to get a much more detailed view of some of the unique things that are happening inside the Earth. So just to point out some of these interesting and unique features, I have the animation here on the left, which shows some of the main results from the French and Romanowitz study, and the image here on the right, which I took from Garnero and McNamara. Some of the large-scale features that you're seeing here are unique objects that have started to have been routinely recognized in seismic investigations. So one of the things that really jumps out right away are these red features that you see in both images. The red color indicates slower than normal seismic velocities, and these big features are known as large low shear velocity provinces, or LLSVPs, which you can see from the animation are roughly antipodal. One is positioned beneath Africa and the other is beneath the Pacific. The footprint, or the lateral extent, of the LLSVPs is very wide. It's sort of continental scale in size, and they extend upwards of at least 1,000 kilometers, if not more, above the core-mantle boundary. We also have very large-scale fast seismic anomalies, such as shown here on the right-hand side of the screen. And these are thought to be associated with subducted slabs or former oceanic lithosphere that, again, has been recycled and subducted back inside our planet. If we zoom in a little further, we start seeing evidence for a whole slew of other very interesting features, particularly in the lowermost part of the mantle, the bottom several hundred kilometers or so. And some of these are not nearly as big as the features we just talked about. Indeed, they have scales sort of on the tens of kilometer scale. So there's a lot of different features going on here, but what we're starting to recognize is that the deepest part of our mantle is actually host to a range of all different kinds of sizes. And the deep mantle might be just as interesting, anomalous, and varied as the structures we see here at and near the surface. And so we're really starting to get a nice look at some of these different features down near the core-mantle boundary.
Samantha,
yeah.
Could you show your pointer? I think the audience cannot see your.
Can
okay.
Okay.
I'll try to
wiggle it around a little bit to make it bigger.
Okay.
So
could you change it to laser, if possible?
Sure. I just got to figure out how to do that. Let's see. Pointer options. Oh, we don't want that. Visible. That's not helping. I don't immediately see how to fix this. Laser pointer. Is that better?
Yeah.
Now I see it. Okay.
It's better. Yeah, go ahead.
So this is just another representation of what might be going on in the deep Earth. And again, you can see there's a range of different seismically unique items down there that we could spend some time talking about. But as I already mentioned, today I'm going to focus on what are known as ULVZs, or ultra-low velocity zones, which are shown by this gold color in this cartoon. So what are ULVZs? As the name kind of implies, these are anomalies that are associated with drastic reductions in both their P and S wave seismic velocities. As noted down here on the bottom of the slide, P wave velocities can move up to 20% slower within ULVZs, and S waves are even more reduced, in some cases up to 50%. It's also been suggested that ULVZs may be associated with increases in density, up to about 20%. The thickness of ULVZs tends to be in the sort of tens of kilometers range, at least in most studies, though thicknesses from 5 all the way up to 100 kilometers have been reported. And as far as their width or lateral extent, you can see, again, fairly wide range here, anywhere from about 100 to 1,000 kilometers. So we know that ULVZs are present in the deep mantle. We've imaged them, at least in some locations, above the core-mantle boundary. But given these wide ranges of these characteristics, from study to study, and the disagreements about, the ULVZ structure, there's been a lot of questions put forth as to what is the origin or the source of ULVZs. So one potential origin for ULVZs are thermal anomalies along the core-mantle boundary, possibly associated with some degree of partial melt. And this comes about from several studies that suggested the imaged ULVZs that they saw had a 3-to-1 VS to VP reduction ratio. So this is about the amount you would expect your S&P waves to be reduced if you had some type of partial melting present. Additionally, some investigations have suggested that ULVZs are spatially correlated with mantle plumes, such as that shown in the image here on the left. This is taken from the Wana Romanovitz 2017 study. And in their case, they were advocating that hot, partially molten ULVZs, shown here in dark red, may actually feed these mantle upwellings. Of course, the temperature near the core-mantle boundary is very high, but the pressure is as well. And so usually, if you're going to induce melting in this environment, it's suggested that you need something like a volatile, perhaps water, or maybe some kind of local shear stress variability to get that kind of partial melting. But again, this is one possibility for ULVZ structure. That said, not all ULVZs have been identified in what are thought to be hot portions of the lowermost mantle. Indeed, some appear to be in presumably relatively cooler areas. And so in those cases, typically compositional anomalies are invoked to represent ULVZs along the core-mantle boundary. Now, under the umbrella of compositional anomalies, that can mean a variety of things. For instance, we might have some sort of iron enrichment taking place in the deep mantle. That may occur due to chemical reactions between the silicate mantle and the iron-rich outer core, which could lead to iron-enriched material along the core-mantle boundary. Or certain mineralogical phase changes, such as that from perovskite to post-perovskite, can also lead to iron enrichment, such as that illustrated in this top cartoon by Mao et al. And in both cases, by having enriched iron content, it actually lowers the shear wave velocity and increases the density under deep mantle conditions, which are both characteristics of ULVZs. So perhaps this is a possible source. Alternatively, it's also been suggested that subducted materials that have reached the deep mantle could potentially be a compositional source for ULVZs. The other image shown here at the bottom was taken from Hiroshi 2006. And what they were looking at is how the density of mid-ocean ridge basalts, or MORB, changes with depth. So the takeaway here is that subducted MORB in deep mantle conditions is actually denser than the surrounding background mantle. I'll also note, though that's not shown in the image, that MORB is also thought to have a lower solidus melting temperature near the core-mantle boundary than the temperature conditions that are expected in those locations. Another idea that kind of falls under the umbrella of compositionally distinct material is the fractional crystallization of a basal magma ocean, or a BMO. And to illustrate this idea, I borrowed this from Dr. Zhang's 2016 paper. Just to clarify, though, that paper was focused on those large low shear velocity provinces that I mentioned earlier. It was not focused on ULVZs, but I thought it was a nice cartoon to try to illustrate the concept. So the idea behind this basal magma ocean, or BMO, is that very early in Earth's history, there was a magma ocean, or a layer of magma deep in the mantle above the core. So this is a very ancient reservoir of material. Over time, as that material segregates and minerals precipitate out of this ancient dense melt layer, it's changing both the composition and the texture in the base of the mantle. So it could be the case that some of this ancient kind of mushy melt, if you will, may still be present along the core-mantle boundary, and perhaps that's a source of ULVZs that we're seeing today. Oops. So I'll also mention that it's been suggested ULVZs may have some type of connection to those large low shear velocity provinces, the LLSVPs, that I mentioned earlier. The image here on the left is a tomographic model from Ritz et al. 1999 at 2,800 kilometers depths of the very bottom of the mantle. And these two large red areas that you see, which are labeled, are again those two antipodal large low shear velocity provinces. The other image here, this is the same cartoon I showed you earlier, or at least a little snippet of it. Again, you can see this red feature, which is one of the LLSVPs, but also point out this little yellow patch right here labeled ULVZ. And so you can see that it's right at the edge of the larger scale anomaly. So it's been suggested that many ULVZs are either within or along the edges of the larger scale LLSVPs. And mantle convection simulations have illustrated that compositionally distinct ULVZ materials may actually be moved or swept by convection currents along the CMB and may accumulate along the boundaries of the LLSVPs. So lots of different ideas about what might potentially be causing ULVZs. So what's the problem? Why don't we know what these are? Well, part of the trouble comes from we don't have a terribly complete picture of what's happening in the lowermost mantle. The maps here were modified from Ewan Garnero 2018, who at the time put together all of the different ULVZ studies that had been conducted to try to see where we see ULVZ evidence and where we don't, and where has yet to be sampled. So as illustrated here, the pink areas on the maps are those large low velocity provinces that we've talked about several times now. The gold areas indicate where they investigated the deep mantle for ultra-low velocity zones and found evidence for them. So again, the gold patches here are where they think they see ULVZs. The areas outlined in red might show ULVZ evidence, but it's a bit uncertain or complex, so we're not completely sure. And those outlined in blue are those that were investigated, but the studies did not find any evidence for ULVZs in those regions. So you can see that our coverage is kind of patchy, right? At least at the time of this study, only about 20% of the core-mantle boundary had actually been investigated for ULVZ structure. If we take a slightly different view and look at the map here on the right, same map with the same type of symbols, but this is what our planet looks like from the bottom up. So this is Antarctica here in the middle. The center of the map is South Pole. And you can see how the continent is positioned in relation to, this is South America right here. There's New Zealand and Australia. And here's the tip of Africa pointing down to Madagascar, just to orient yourself. So you can see, while again, ULVZ studies are fairly sparse across much of the planet, this is especially the case beneath the southern hemisphere. Deep Earth investigations under this part of our planet are very, very limited. So why focus on this particular area? In other words, why investigate ULVZs beneath Antarctica and the surrounding southern hemisphere? There's a couple of reasons we opted to do this. First, as I showed on the previous slide, even compared to the rest of the CMB, which in and of itself is not terribly well sampled, the southern hemisphere in particular is really sparse when it comes to such studies, dramatically undersampled. And so there's room here for some very interesting new discoveries. Perhaps a little more interestingly and important is the sort of the unique characteristics or the unique environment that this area presents. And that's shown here in the image on the left. This is another tomography image taken from a somewhat more recent study, again, right at the base of the mantle. And these purple dashed lines that you see here, again, are those LLSVP boundaries that we've talked about before. So what you're seeing here is that most of Antarctica and a lot of the surrounding southern hemisphere is highlighted in this blue or seismically fast coloring. and it's away from the two antipodal LLSVPs. Also, Antarctica itself is not actually associated with any present-day subduction systems. And so this actually makes this portion of the lowermost mantle quite a unique environment in which to study ULVZs. Also, stations across Antarctica record quite a lot of earthquakes. They have almost complete azimuthal coverage, partly from subduction systems in the Pacific, but also from what's known as the Circumantarctic Ridge. And so together, these earthquakes and stations provide fairly nice coverage of the lowermost mantle to do such studies. So today I'm going to talk to you about two different studies that my group has been working on. And both of these are focused on what are called PCP waves, or core-reflected P waves, that you can see by the heavy blue arrow here in the images on the left. So the wave comes in as a P wave, it reflects off the core-mantle boundary, and then proceeds as a P wave on its way. What's interesting about waves like PCP is if a ULVZ is present, this green layer here, okay, we can get some other arrivals associated with the ULVZ showing up in our data that can tell us about that structure. So for example, we have this wave here labeled PDP. That's a precursor or a wave that's going to arrive earlier before the main PCP phase and is associated with a reflection off the top of the ULVZ. We also have these other phases that are shown in both panels that are associated with waves that reverberate or bounce around inside the ULVZs. And these are going to generate postcursors or signals that arrive after the main PCP phase. So if we can identify precursors and or postcursors, we can actually model these phases to learn about the corresponding ULVZ structure. And so both of the studies I'm going to tell you about today are employing this kind of data. Over here on the right, these are the stations that we've used for the two studies. Our earlier study, which was published a few months ago in Science Advances, used the network that you see in the top map here. This is what's known as the TAMNet array. It happens to be an array that I ran between 2012 and 2013. So my team and I deployed these stations. And you can see where the array is located within the broader scale context of the rest of Antarctica. So this is our first study. And then more recently, we've expanded our investigation to use all of the seismic stations across Antarctica. And those are shown by the red triangles here on the bottom map. So I'll be showing you results from both of these today. Using PCP can be a little bit tricky, and the image in the middle is trying to illustrate why that's the case. So in this middle panel, you see the ray paths of the direct P wave, as well as that core-reflected PCP wave that we were just talking about. The small pink box is highlighting the area near the core-mantle boundary where a ULVZ could potentially be present. I'll also point out this wave right here, this dashed gray line labeled PKP. This is a seismic phase that's a P wave that then continues and traverses or moves through the outer core. And actually, a lot of the P wave energy at the core-mantle boundary continues as a PKP wave. And so what this means is that the amplitude of our PCP arrivals can be quite small. To illustrate this, these traces here on the right show the main direct P wave, as well as the PCP wave for just one example earthquake recorded by one of the Antarctic stations. And you can see the pretty dramatic difference in their corresponding amplitudes. PCP is here, but it's not the largest amplitude signal. And so because of that, and the potential to have a lower signal to noise ratio, this phase can be a little tricky to identify and then to interpret. So in order to reliably interpret ULVZ structure using this phase, we need to have robust waveform stacks or waveform averages to work with. So with that in mind, we developed what's known as the historical interstation pattern referencing, or HIPR approach. I don't really have time today to get into all the details of the HIPR method, but I will just summarize to say that we use travel time and data quality measurements across the entire data set to establish historical patterns for these different parameters. Then by taking an individual waveform and comparing it to that historical set, we can develop both event and station weights that better reflect the quality of our individual waveforms. So these weights can then be applied to the waveforms themselves, and we can use this to improve our waveform averages or stacks to improve the data we have to work with for ULVZ investigations. The image here on the right just shows an example of this type of stacking. So these first 15-ish traces or so, the top ones here, the left side, these are the P wave arrivals, the direct P wave arrivals. These are the PCP waveforms on the right. The second to last trace, the one with the cursor here, those are the original P and PCP stacks. And then the bottommost traces are the HIPR-based P and PCP stacks. And particularly for PCP, you can see that this approach really helps to improve the signal to noise ratio of this PCP signal that we're interested in. Again, if you're interested in knowing more about the HIPR method, I would point you towards our 2021 JGR paper. So I'm first going to talk about the first study we did, focused just on that one array, that TAMNet array, and then we'll move into the broader scale study in just a few minutes. So with TAMNet, we looked at a variety of PCP waveforms recorded by that network. And in that case, we were stacking or averaging individual earthquake waveforms. So for a given earthquake, we were stacking all the records for that particular event. This is another example of those waveforms and the corresponding HIPR stacking I was talking about just a minute ago. Again, the left is the P wave arrivals. The right is the PCP, again, at the different stations. Each one of these is a station name. And the bottommost trace here are the corresponding HIPR-based P and PCP stacks. This trace is blown up and made a little bigger here in panel B, and that's what the black line is here in the background. So that's the observed PCP signal, observed PCP stack. The arrow here, which I'll point out is also right there, that bump that it's pointing to, that's one of those ULVZ precursors that we're looking for. So these are the kinds of signals that we're trying to model for ULVZ structure. The two other lines on panel B show the results of synthetic modeling. The green dashed line, as it says right here, is from the primary reference Earth model, or the PREM model, which does not contain a ULVZ. And the red line is a synthetic we made that does include a ULVZ, and this was the synthetic that fit our data the best. So these values right here are the corresponding ULVZ characteristics that best fit this particular stack. In other words, a ULVZ that's 20 kilometers thick with a 30% S wave velocity reduction, an 11% P wave velocity reduction, and an increase in density of 20%. Just to finish out for completeness, this panel here, panel C, the histogram here is showing what we refer to as comparison quality, or CQ values. Again, I don't have time to get into all the details of this, but basically this is a measure of how well our synthetics fit our data. And just for reference, right here is where the PREM model, the non-ULVZ model, would land. And here's that best average where it fits. So quite a big difference between the two. The scatter plots here on the bottom, I'll show you some other examples of these in just a minute. But basically, these are the top 100 best fit models for this particular signal. So we applied the same type of approach to all the PCP data recorded by the TAMNet array. And then looking at our results, we enforced various criteria to not only check that our synthetics fit our data well, but also to check if a non-ULVZ model and a ULVZ model, how well did each one of them work? In other words, does a model that has a ULVZ fit the data markedly better than one without a ULVZ? And so this ultimately led us to classify our events as either being robust or uncertain. The red dots in the map here on the right show the average PCP bounce points for the events that we examined, and these events met all of our criteria to robustly show ULVZ evidence. The yellow dots are also average PCP bounce points, but they didn't quite meet all of our criteria for robust signal, so we're indicating them as possible but uncertain ULVZ evidence. The colored polygons that you see in the background and the different abbreviations here, you don't need to worry too much about what those are, but I'll just note that we separated our events into different geographic families, again, the colored boxes, and then within each family, we grouped the PCP bounce points or reflection points off the core-mantle boundary using a 2-degree radius bin, and we kind of averaged out the values. And we did this in order to look at variations in the ULVZ characteristics as we move from one location to another. So I know this plot is a tad busy, but bear with me while I walk you through it. Over here on the right, these are the best fit ULVZs for each of those geographic families that I showed you on the previous slide. Again, here's the corresponding little key just so you can see how the colors match. The bottom plot here shows the change in P wave reduction versus the change in S wave reduction in the ULVZ. The top image, the horizontal axis, is ULVZ thickness, and then the vertical axis is velocity reduction. Those with solid error bars are for shear wave reduction, and those with dashed error bars are for P wave reduction. And then the corresponding error bars are one standard deviation to the average. So right away, yes, there is overlap with an error, but even with that uncertainty, we are seeing evidence not only for ULVZ structure in our study area, but variability in that structure. Now, that said, we do have to acknowledge the fact that we have some issues with trade-offs in our modeling, and this is what's illustrated in the bottom image here. Panel A, just to point this out, this is another example like the one I showed you previously, where the black trace is the observed PCP stack. The green trace is the PREM synthetic, in other words, the model that does not contain a ULVZ. And the red trace is the best fit synthetic that does contain a ULVZ. These are similar to the scatter plots that I already showed you. It's just the symbols are a little different. In these cases, we've color-coded them and sized them depending on what density increase was used. But you'll notice these very obvious linear trends. And this is not uncommon with 1D modeling. It's very possible to get a thicker but less anomalous ULVZ fitting your data equally well as a thinner, more anomalous ULVZ. And by anomalous, I mean a bigger or a smaller velocity reduction. So these trade-offs between thickness and velocity can make it kind of tricky to pinpoint the specific ULVZ characteristics in any one location. But again, I just would like to point out that we are showing evidence that there is ULVZ structure beneath the southern hemisphere with some indication that we are having variability in that structure from one location to another. So I'm going to change gears just a little bit now and get into the second study that we've done. And this is the one using all of the stations across the continent of Antarctica. Just like with the previous study, we are still using those PCP waves. And we've divided the Southern Hemisphere study area into 2-degree radius bins. And then we identify which PCP bounce points fall within each of those geographic bins. Within each bin, we then perform what's called double array stacking, and this is illustrated in the cartoon here on the left. So the brown area here is meant to represent the core-mantle boundary. Each one of these green ellipses is a target depth at some position above the CMB. And so what we do is at each of these target depths, we take all of the reflection points, the PCP reflection points at that particular depth, and we stack them together. And we repeat this for various depths moving upward from the core-mantle boundary. So PDP here, hopefully you recall you've seen that before, that's a reflection off the top of a ULVZ. In other words, if a ULVZ is present and the top of that ULVZ coincides with one of these target depths, with one of the green ellipses, we would expect to have a coherent signal that's going to constructively stack out and show up as a higher amplitude in the double array stacking. Conversely, if there's no structure there isn't a ULVZ present, the signals are going to destructively interfere and lead to a lower amplitude. So by doing this from one bin to another over the whole study area and at these various depths, we can map out variations in the ULVZ structure across our study region. The image here on the lower right is an example of what one of the outputs looks like for one of the geographic bins we've examined. The black trace here is the double array stack output. So notice the horizontal axis here is the height above the CMB corresponding to each one of these green ellipses. And the vertical axis here is the normalized energy or normalized amplitude at each one of those points. And you'll notice this bump right here, okay? This main peak right here is the PCP reflection off the core-mantle boundary itself, but we have this additional bump at about 30 kilometers or so above the CMB. These are the kind of features we're looking for. So we take this a step further, and then we also employ synthetic modeling to try to get at what the corresponding ULVZ characteristics associated with this structure might be. So all of the gray as well as the red line here are synthetic results, synthetic double array stacking results from different ULVZ models. And the red line happens to highlight the model that worked best for this particular example with a ULVZ that has a thickness of 32 kilometers. And these other values you don't have to worry about too much, are just some of our statistics related to the fit of the synthetic to the data. So this is work that my graduate student, Coyote Abdullah, has been doing, and we are very close to getting this put together to submit for publication. I'm hoping the paper is going to get submitted within the next week or two. So we repeated the double array stacking, like I showed you on the previous slide, for all of the geographic bins across the study area. And the images shown here actually compare the results of the full all Antarctic station study, again done with the double array stacking technique, to the earlier study just done with TAMNet. Right? So each one of the panels here corresponds to one of the geographic families that we defined in the earlier study and that I showed you on the map before. The red dots with the error bars are the results from that earlier study, showing the average best fit ULVZ characteristics for the family that's indicated here in the upper right. The black triangles with the error bars are the results from the broader scale study using all the Antarctic stations, and basically using both shear wave and P wave velocity values or reductions that are comparable to the earlier study. And then we're comparing how the ULVZ thickness compares between the two results. So you can see these actually match quite nicely, especially if you take the uncertainty into account. We're getting a pretty darn good comparison between the robust results we got with the TAMNet study and the individual earthquake analysis and those with the broader scale investigation using the double array stacking. So this is really encouraging, and it's nice to see consistency between the two investigations. So the map here on the right kind of summarizes the results of both studies together. As it says in the legend here, the circles correspond to either events or bins that showed robust ULVZ structure, met our criteria, and says, yes, there's definitely a ULVZ there. The diamonds are associated with either complex, and I'll come back to what that means in a minute, or uncertain ULVZ structure. Yellow and pink symbols are from the first study just done with TAMNet, and the orange circles and the purple diamonds are from the more recent study using all the Antarctic data. So broadly speaking, both studies show widespread evidence for ULVZ across the Southern Hemisphere, beneath Antarctica and these surrounding regions. And again, both studies show evidence that the structure is variable, that the thickness of the ULVZs is not the same everywhere. It varies quite a bit. Also note, particularly in this most recent study, and again, this comes back to these purple diamonds, some of the double array stacking results, or the DAS results, showed what we classified as complex findings. And these were double array stacks that we could not fit with a 1D model. So this might indicate that the ULVZs have some kind of internal structure, either a layered velocity structure or some kind of gradational velocity with depth that, again, we can't model with a 1D input model. So in order to get at this complex structure, more advanced modeling would be needed. But we're seeing really good evidence for ULVZs across the whole Southern Hemisphere study region. The background on this map is the same tomography I showed you a little earlier in the talk, and I'll just reiterate that the majority of our ULVZ detections are within this seismically fast, the blue color, which is associated with sort of presumably cooler material in the lowermost mantle, again, away from the LLSVPs, or the purple dashed lines. So hopefully I've piqued your interest that we've found widespread ULVZ evidence in this area. And of course, this sort of begs the question of, well, what's causing these things? Come back to the question of origin. So let's revisit some of the different ideas that have been put forth as the source of ULVZs. This is the cartoon I showed you earlier by Juan and Romanowitz in relation to the suggestion that ULVZs may be associated with thermal anomalies along the core-mantle boundary. But as I mentioned in the previous slide, our investigation is really focused in a seismically fast, again, presumably cooler portion of the lowermost mantle. And so thermal anomalies alone probably aren't the best explanation for the ULVZs that we're imaging. We also had the BMO, or the basal magma ocean idea that was put forth for ULVZs. And again, here's the cartoon from Dr. Zhang's work. While BMO materials very likely could create LLSVPs, and that's actually what his study focused on, again, it was suggested that perhaps the same kind of material might still be around on the core-mantle boundary today, even though this is very ancient material, and that they could be a source for the ULVZ structure. That said, if that's true, we need to have some kind of mechanism to keep that BMO material from becoming entrained into the LLSVPs, especially considering that convection has been happening presumably for billions of years on our planet. So it leads to questions about how much of this BMO material still exists outside of the LLSVPs. We also talked about potential compositional sources for ULVZs associated with iron enrichment, again, either from chemical reactions between the silicate mantle and the iron core, or associated with mineralogical phase changes. But these types of reactions are not only pressure dependent, but they're also temperature dependent. And so if this was the sole origin of ULVZs, we would expect to see the thinnest ULVZs outside those large low shear velocity provinces where the temperatures are cooler, and then the thickest ULVZs within those larger scale anomalies where the temperatures are thought to be much higher. But this kind of thickness pattern isn't observed with ULVZs across the planet. So this kind of brings us back to the idea of subduction and subducted materials in the lowermost mantle. And as you may recall, I told you earlier in the talk that Antarctica is not actually associated with any present day subduction system. But subduction around the Pacific Ocean, the circum-Pacific subduction system, has been ongoing for millions of years. And so this kind of begs the question of whether or not subducted materials might be able to explain the ULVZs in our study region. Again, just a little reminder, this is the image from Hiroshi 2006 that emphasizes that subducted moor mid-ocean ridge basalts are denser than the surrounding lowermost mantle. And again, they also have a lower solidus melting temperature. So could this be the source of the ULVZs we're looking at? So my colleague Mingming Li, again, who's at Arizona State University, put together a geodynamic model that I'm going to show you here in just a minute to try to assess whether subducted materials from adjacent subduction systems might be able to move and spread throughout the southern hemisphere and ultimately there explain the ULVZs that we're seeing. So I'm going to start this animation here on the right in just a minute, but just to set this up, each of the arrows here is a vector indicating the direction of mantle flow in the lowermost 50 kilometers of the mantle, so 50 kilometers above the core-mantle boundary. The way these models work is Mingming introduces these passive tracers into the upper mantle that then are subducted and move with a convective flow. So you'll see colors starting to show up here when I start the animation. As it says, those colors represent the number of tracers, which are a proxy for subducted materials. So the more color you see, the more tracers there are, and hence the more subducted material. So hopefully I can get this thing going. There we go. So this animation runs from about 500 million years ago, excuse me, up until present day. And you can see the colors starting to show up here as the tracers or the subducted material enters the lowermost mantle. Where they're kind of blue in color, we have a lot of material. Where they're a little more brown in color, there's a little less material. So in other words, the accumulation of the subducted material is quite variable across the core-mantle boundary. And you can see how this shifts and moves around with time as that subducted material is pushed around by the convection currents. So I'll just let this get finished running. So this is stopped at present day. And what's interesting here is we see that the entire lowermost mantle or the entire core-mantle boundary is blanketed in this subducted material. It's kind of all over the place. And this particular animation is only run for, again, about 500 million years, but presumably convection inside our planet may have been ongoing for billions of years. And so it's possible that the entire core-mantle boundary, the entire lowermost mantle, could be blanketed or covered in this type of subducted material, and perhaps even lead to a ubiquitous ultra-low velocity zone. So I just want to take a minute and come back to those complex ULVZs that I mentioned. These are the ones that we could not fit with our 1D modeling, and again, may indicate some kind of variable vertical structure inside the ULVZs, either some type of layered or gradational velocity structure. As I've mentioned a few times, MORB has a lower solidus melting temperature than the temperature conditions expected at the core mantle boundary. So it's very possible for some of this material to partially melt under lowermost mantle conditions. If you have hydrated subducted ocean sediments or hydrated lithosphere, that material could push the solidus melting temperature even lower. And additionally, Ming had a study that came out just a few years ago now that showed how in subduction influenced regions of the lowermost mantle, it's actually possible to get localized thermal ridges forming. So collectively, this indicates that subducted materials, again, can undergo some degree of partial melting in the deep mantle. So perhaps our complex ULBZs still fit with our interpretation of subducted materials. It may just be that localized partial melting of that subducted material is leading to this more complex vertically variable ULBZ structure that we see in some locations. So just to kind of wrap up here, our study has looked at PCP waveforms that have been recorded by stations across Antarctica. And we've analyzed these waveforms with two different approaches, one based on just the TAMNET array and individual earthquakes, and the other with all the stations across Antarctica. And collectively, these studies indicate widespread evidence for variable ULBZ structure beneath Antarctica and the Southern Hemisphere. We would advocate that ULBZs might predominantly be associated with subducted materials along the core mantle boundary that may also be experiencing some degree of localized partial melting. As far as additional challenges and questions outstanding, I mentioned these modeling trade-offs that make it a bit difficult to specifically determine the ULBZ characteristics in any given location. And this is still an issue whether we're doing the individual network assessment or the double array stacking. Also, this question has come up about whether ULBZs are ubiquitous kind of everywhere along the core mantle boundary. So to take this work further, we have plans to develop both our seismic and geodynamic models a little bit further. Specifically, we would like to look at other core reflected phases, so not just PCP, but phases like SCP, SCS, maybe PCS, to use this as a different way to look for ULBZ evidence. And why that's useful is because different seismic phases have different sensitivities to lowermost mantle structure. So by modeling all of these and comparing them to each other, we might be able to mitigate some of those modeling trade-offs. Additionally, we'd like to do more extensive geodynamic modeling, kind of building on the animation I showed you from Ming Li, and incorporating mineral physics constraints into those models. And together, this would be really powerful because this would help to provide details on both the distribution and characteristics of different possible ULBZ sources. And then we can also evaluate how the ULBZ properties are expected to vary both spatially and temporally. So as shown in the flowchart here on the left, by coming at this problem with these different techniques, we're hoping that we can get a better handle on what the source of ULBZs are. I'll note that we actually just submitted this proposal last week to the National Science Foundation, so it is currently pending review. So with that, I'm going to wrap up, and I'm happy to take any questions that you guys might have.
Thank you very much, Samantha. Now it's time for questions from our participants. So feel free to raise your hand or open your mic. Otherwise, you can also leave a question in the chat, and I could read the questions on your behalf. So go ahead.
Hi, I guess I will start. Hello, Dr. Hansen. Thank you for the very interesting talk. I'm a seismologist, but mainly working on mantle transition zone and above. So kind of new to this kind of depth domain. A few questions. The first one, actually, the second last slide's future works partially answer my question. So I'm just wondering, why not SCS? Why did you decide to use PCP? in this study. My understanding, SCS had higher amplitude, so presumably it's a bit easier compared to PCP.
Yeah, that's true. There are some historical reasons why we kind of started working with this particular phase. I had a student who got interested in looking at this, and so because they kind of started down this path, we sort of just took it and ran with it. But you're right. I think SCP, SCS, both of them have very possible good contributions that could come into this to help investigate this structure. One thing we did find, and that was just with the TAMNet array, not the full Antarctic network. But when we started doing the initial project, given the event station distances we were working with that particular array, the SCP sampling across the lower mantle was much less than the PCP sampling. And so that's part of the reason we decided to start with PCP, even though it is a bit of a challenging phase to work with. But now that we've kind of gotten our methodology built with the double array stacking, I think it'll be fairly straightforward to kind of expand this work using all the stations and taking on these other phases.
Okay, thanks. And also it's kind of a related question. So do you expect different processing results or imaging results using another phase? For example, like mantle transition zone study, and people, see a clear MTZ using SS precursors, but for PP precursors and for some region at least, 660 is not observed using PP precursor. So
yeah, I think there's definitely the likelihood that they're going to have variability, and to some extent we do expect that, because again, they have different sensitivities to the different ULVZ characteristics, right? So SCS, for example, kind of the advantage of SCS is that it gives you an independent constraint on S-wave velocity or S-wave velocity reduction, independent of P and SV, right? But usually the frequency content of SCS is a little bit different. So you're not getting quite the fine scale details that, say, PCP or SCP can give you. SCP and PCP have sensitivities to both P and S wave velocity reductions. So in theory, by putting them together, you should be able to sort of bridge some of these gaps. But are they going to have some conflicts? Probably, and we'll have to deal with trying to figure out what's causing that. The other thing that's probably worth pointing out is all of these phases do have some overlap where they will sample the same parts of the CMB. But of course, they are different phases, they have different paths. And so from a given earthquake, you're not necessarily going to have all of these phases sampling all the same parts of the lowermost mantle. And so we've been looking into, where we're probably going to get the most coverage. And I think for those areas where we do have a lot of sampling, we can get a little more creative and a little more advanced as far as our modeling goes.
Okay. Yeah, thank you. Yeah. Maybe could I ask one more question?
Yeah, that's great.
Yeah. So it's quite interesting imaging result, especially the recent study, the paper you're going to submit, kind of confirm your previous work, which is great. But also I noticed that for actually a lot of areas, the kind of the two kind of different groups, like those kind of uncertain. You have like diamonds and circles. Yes, this is true. Yeah. So one is uncertain, right? Diamond means uncertain, and circles means like robust ULVZ imaging result. They are kind of overlapped for most of their. So do you have any comments on this?
So maybe I need to clarify this just a little bit. With the earlier study, the Hansen et al. Study, we had these certain criteria that we enforced we basically separated the data into, yes, this shows robust ULVZ evidence, or it might, but we can't really tell. And so at least for the first study here, that's the difference between the circle and the diamonds, the yellow circles and the pink diamonds. a lot of that just had to do with the quality of the data. If you have a very thin ULVZ, it's hard to differentiate that from no ULVZ because our resolution for really thin structure is a bit limited. So anything less than about 5 kilometers, we're probably going to have a hard time picking up. So you may have a result that doesn't necessarily show very obvious ULVZ structure, but that doesn't necessarily mean it's not there. It may just be too thin to resolve. With the more recent study, which again are the orange circles and the purple diamonds, we kind of came at this from a slightly different approach. It is a different method. And we're actually looking at this a little bit further. I had to talk about this today. But again, in this case, the orange diamonds, again, met our criteria for robust ULVZ evidence. The diamond or the purple diamonds here, I'm going to just jump back to here. This is one particular bin that, I showed you an example of the double array stacking for. In some cases, what we're seeing is instead of having one bump, like in this case, we actually see multiple bumps. So you'll have the main PCP reflection off the core-mantle boundary, and then out here you'll have multiple peaks showing up, indicating you have multiple layers going on. So there's, different structure that's vertically variable. And so the purple diamonds in this map are those that, again, couldn't be fit by this 1D model because we're just treating the ULVZ as just one big layer, right? Why are they mixed together? That is an excellent question. And right now, like I said, my best thought on this is if they are associated with subducted materials, which is something we need to investigate a little further, it could be that in some locations, not only do you have this compositionally distinct subducted material that you're looking at, but because MORB can also fairly readily undergo partial melting, at least in some conditions, it could be that because you have both partial melt and this compositional subduction material there, that's creating this vertical variation in the structure. So perhaps, where we have these diamonds, you have some kind of local partial melting going on in the subducted materials and maybe less partial melting in the places we see simpler structure. It's a running hypothesis. And again, it needs further testing, but that's kind of my best interpretation right now.
Yeah, it definitely needs more advanced modeling techniques to distinguish this. Yeah. Okay, thank you very much.
You're welcome.
The next question, please. So another question, the last question was from Professor Yingfeng Chen at Zhejiang University, China. The next question is from HP Star in Beijing, Professor Zhenbiao Tao. And the question is about geodynamic model in the recent publication in Science Advances. What is driving force for the horizontal flow from the cold subducted slab area to the hot LVP piles area at the core-mantle boundary?
So thanks for the question. When Ming set up the models, he's the one who created those. He used plate tectonic motion history over the last several hundred millions of years to drive the system. So he's using, I think it's Seton et al.'s 2012, I believe, is the reference. He's using their plate tectonic model to drive the convection field. And then the tracers, as I said, are introduced in subduction environments in the upper mantle. And then as the convection model runs, they kind of get carried along and pushed around following the convection currents. The tracers themselves have no density anomaly associated with them. They're just moving along for the ride. And so part of what we would like to do, assuming our proposal gets funded, is to build more elaborate models. He's going to work with, this is where Sang-Hyun Shim comes in. He's a mineral physicist. And so together they can build convection models that incorporate, more accurate mineral physics characteristics, things like segregation of subducted materials on the core-mantle boundary and things like that, which are not in the current models. So there, again, there's definitely room to further develop the project, but it was really interesting when he ran these and we got the results back to be like, wow, this stuff's kind of all over the place. And the accumulations of subducted materials in the model are real variable, just like the ULVZs seem to be quite variable. So causation, but the combination is kind of intriguing.
Okay, next question, please.
Hi, Samantha. Thanks for your very nice talk. Can you hear me?
Yes, hi.
Oh, hi. I'm Tim Yang from StarTech. I worked on geodynamics, so I also have a question about Mingming's animation.
I will do my best.
So, as you see from this slide, there's a blue ring beneath the Antarctic and Australia, South America. So in the Mingming's animation, I do not see very many downgoing tracers beneath Antarctic. Is there any reason why is that? Or maybe just the tracers is not the part, maybe 10 million years, 100 million years. The tracers, the downwelling tracers are from the part of 500 million years. I mean, it's not it's a long time ago, not just the past several hundred million or very short time.
Yeah, we have to be a little careful about making a direct one-to-one comparison between the output of the geodynamic models and where we're seeing ULVZs, because again, it's a proxy. These are passive tracers. So where they specifically end up in the geodynamic model may not actually be where that material is today. It's just an approximation. The other thing I'll mention is the animation I showed from Mingming's work is one of two models that he presented, both of which are attached to the Science Advances paper, and you can download those, the movie files. We made them available. The other model that he made is a little bit different than the one that I showed, because it actually includes the two big LLSVPs in the model. They're treated differently as large thermochemical piles. And when those are introduced into the model space, it does affect where those tracers end up and what the distribution of the subducted materials is a little bit further. So I don't have it right here available, but if you want to watch the other movie, like I said, it's available online, or I can send you the link. And so the pattern is quite a bit different. We do ultimately, though, either model you end up with, you do still end up with a fair bit of material in the lowermost mantle. And again, it has this variable structure that we're seeing. So again, it's kind of an intriguing comparison between the two. But again, at this stage, I'm a little hesitant to say this pile of accumulated materials in Mingming's model is this ULVZ. We can't make that kind of direct one-to-one comparison. I'm not sure if I answered your question.
Yeah, that answers my question. So the other question is about the delta rho, the density variation you inverted. So how did you constrain the density? Of course, I only saw from the waveform modeling, they are only about the travel time. Why can you also constrain the density anomaly of the ULVZ?
So density is actually kind of a tricky thing to constrain. A lot of the studies that I'm going to jump back to a different slide here for just a minute. These are, again, we have these trade-offs we have to worry about, and to some extent density plays into that a little bit. But if you can find a ULVZ model that has a particular density variation, a particular velocity reduction, and a particular thickness that fit your data well, you might be able to make a case for this. Seismic waves do a much better job constraining velocity variations than density. Density is a tricky thing to nail down. Actually, in our work, we didn't see a lot of variability with density, and we don't actually talk about that very much in the paper. I think if you really wanted to nail down density variations, you'd have to do a lot more extensive three-dimensional modeling than what we've done so far. But the bulk of what we're going to be able to constrain, at least with our methods, are seismic variations and changes in dimensions and velocity. I think a lot of the estimates for ULVZs having an increase in density comes back to high temperature pressure geochemical or mineral physics experiments that, if, for example, let's say ULVZs were associated with, perovskite to post-perovskite change or some kind of chemical reaction at the CMB, those investigations suggest that those kinds of materials would have a higher density. So I think a lot of the density constraints are not necessarily coming from seismology, but from these other kinds of deeper studies.
Thank you. Thanks again for your nice talk.
Thank you.
Are there any more questions? You will do last one or no? Okay, I think we have kept you for really long. Samantha, thank you very much again for giving the talk and interaction with our audience today. So this video will be posted on our YouTube channel, Bilibili channel. So I think more people will watch it. Maybe they're going to leave comments in the channel.
I'm happy to take questions. Just send me an email.
Yeah, I bet people will. Okay, thanks again for your talk, and thanks everyone for your participation. Okay, have a great day. Bye-bye.
Bye.